given a packing, we can talk about how uniform it is, where we define the uniformity to be the radii ratio of the minimal disk over the maximal disk. And obviously, over the plane packings, the hexagonal packing is the most uniform because its ratio is just 1. You can't beat that. But it's a long-standing problem open problem to actually know what's the second most uniform triangulated packing. Because this is related generally to what kind of radii ratio you are allowed in order to beat the density of hexagonal packing. And today we are going to first talk about the infinitesimal rigidity. So let's first do some reviews on tensegrities. A tensegrity framework, GP, in D space is a complete graph G with vertex and edges, E minus, E plus, E naught, and E empty. We call elements of E minus cables, E plus struts, E naught bars, and E empty free edges. So intuitively, free edges are just not there because they can change in both ways. Cables cannot increase in length, struts cannot decrease in length, and free edges have no conditions. Bars must be fixed. Given the configuration P, if Q satisfies all the length inequalities, we say GP is greater than or equal to GQ. And if at least one of the length is strictly satisfied, we just say, well, GP is greater than GQ. We define a motion as an analytic path that starts from P and satisfies all the inequalities at all time. We say P is rigid if any motion is entirely made of congruent configurations. Then we can ask infinitesimal rigidity. So infinitesimal motion is the derivative of a motion at t equals 0. One can show it is equivalent to a vector P prime, such that the derivative of the length squared, which is given by this, satisfies the inequality we want. If any infinitesimal motion is derivative of trivial motion, we say the framework is infinitesimally rigid. So that's basic definitions from tensegrity frameworks. Infinitesimal rigidity implies rigidity. This should be sort of easy because if it's not rigid, then you take a motion and then take its derivative at t equals 0. If your motion happens to be constant at the beginning, you just move your points. You start with somewhere in the middle. Your motion actually starts to change, and then you take the derivative there. The main tool used to study infinitesimal rigidity is the rigidity matrix, defined as the following. For each, the columns are labeled by vertices, and the edges are labeled by, the rows are labeled by edges. And for each xi item, the entry is xi minus xj. Similarly for yi, and for j's vertex, you just use the minus sign. Here, free edges are ignored because in tensegrity frameworks, they don't do anything. If you have an edge that can become longer and become shorter, you can just ignore that edge. But I'm including this in a definition because in circle packings, having a free disk that can grow and shrink actually changes things. Observe left multiplication by omega gives the vector sum for each vertex. So if you think of omega as a force density, this is the force balance in x and y directions. And right multiplication by p prime gives the dot product. That's the derivative of length at the very beginning. So the kernel of the rigidity matrix are infinitesimal motions that preserves all lengths. So if you compute the rank of the kernel, you get the infinitesimal rigidity of the bar framework, while you assume every edge that is not free is a bar. While the co-kernel consists of self-stress as force density per length, that gives 0 net force on each vertex. Because the left co-kernel implies the force balance on each vertex being 0, and the kernel implies the derivative of the length it being 0. And Roth and Whiteley provided a criterion of when is a tensegrity framework infinitesimally rigid. It happens if and only if two conditions hold. It's infinitesimally rigid when all cables or struts have fixed length. If you replace cables and struts by bars, it must be infinitesimally rigid. Because otherwise, even if all the lengths are fixed, it's still flexible. It can't be infinitesimally rigid. It's possible to assign a force density on each edge so that the assigned number is positive on cables, negative on struts, 0 on free edges, and arbitrary for bars, so that every vertex has a 0 net force. The intuition is that cables are not allowed to shrink. Allowed to shrink, but they are not allowed to grow. So they can hold forces that pulling it longer. So it can hold a positive force. And struts cannot be shrinked, so it can hold a negative force. And motivated by tensegrity, we can define a disk packing rigidity. In disk packing, we have a planar graph G. The graph has to be planar because otherwise you don't have a packing at all. Then we separate the vertex set as V minus, V plus, V naught, and V empty. Here, V minus will be the circles that we want them to shrink or at least don't increase. V plus are the circles that can grow or stay constant, but they cannot shrink. V naught are the circles that we want them to have fixed size. And the V empty are free circles. They can increase in size and shrink in size. And a configuration in this case is in R to the 3V, because for each circle you have an information of where its center is and what its radius is. We say GP is a packing of G if each edge satisfies the length squared equals the sum of radius squared. That says whenever you have an edge, it's tangent. And we want to preserve the orientation of the complex because you can actually flip the entire packing into a triangle if you use a Mobius transform to make one point in a triangle to complex infinity. So we want to avoid that kind of situation. So we want to study packings of only one orientation. We say GP is greater than or equal to GQ if Q satisfies all the inequalities. And a motion is defined similarly. A packing, so if you start with a packing P and you can move along, and along the path you require, they are all packings that satisfy all the constraints. If all the motions are made of congruent packings, you say it's you say it's rigid. So here's an example of a motion. Throughout the presentation, we will label fixed disks green, the disks that want to grow red, and the disks want to shrink blue. So you can see that the red circles are growing, and the blue circle is shrinking, while the green ones stays constant. So that would be a motion on the packing given the inequalities represented by the color. We can study the infinitesimal rigid motion. We can define infinitesimal motion as derivative of motion at t equals 0. It's easy to see infinitesimal motion is a vector p prime, such that it satisfies the length, the derivative of the length being 0. So basically, the pj minus pi, pj prime minus pi prime, take the dot product. It must be equal to the same thing going on with ri plus rj. And we require disks that are at least growing have non-negative ri prime because its radius infinitesimally must stay constant or increase. And the disks that cannot grow in size have negative ri prime, and fixed they have 0 ri prime, of course. We see the packing is infinitesimally rigid if any infinitesimal motion is yielded from a trivial motion. Of course, again, infinitesimal rigidity implies rigidity because you can otherwise take a motion, then take derivative. But does rigidity imply infinitesimal rigidity? Well, the answer is no. And here's a counterexample I find. This packing is rigid, but not infinitesimally rigid. It's probably not easy to eyeball how you can assign a growth factor to each disk or shrink factor so that all the red disks are growing in size, all the blue disks are shrinking in size, while the two gray ones can be anything, they are free. But the infinitesimal motion is actually very easy. If you just assign the growth factor 1 to disk 2 and -1 to 5, that's actually a infinitesimal motion. This infinitesimal motion can keep all other disks constant. This packing on the right is both rigid and infinitesimally rigid. We can define another kind of rigidity matrix for packings that is slightly different from tensegrity. So this matrix have terms, it's the same term for xi, yi, xj, yj, but for ri and rj, the term is all minus ri minus rj. One can check if you right multiply it by vector p prime, it actually uses the infinitesimal packing condition. So the kernel of the matrix are infinitesimal motions when we assume all the disks are free. So in this equation, there's no constraint on how the disk can change. So if you take the dimension of the kernel, it will be, if it's triangular packing, the dimension of the kernel will be the number of boundary vertex plus 3. And the 3 dimension comes from rigid motions. And the number of boundary vertex defines the degree of freedom for non-trivial motions. If you left multiply p by vector omega, then first you use a force balance on x and y. But on R, you have this weird thing. You can interpret it as a polar force sum. So you can interpret this scalar sum as basically you sum up all the outward force, then subtract the inward force as scalars. Hence, the co-kernel can be interpreted as a force density on each edge, so that each disk has 0 net force in x and y direction, and 0 inward out force, and 0 inward outward force. In general, there's no reason to expect the co-kernel to be non-empty. In fact, if your graph is maximal planar, which says if it's a triangulation of a triangle, I think I can prove the co-kernel has to be empty. And the proof uses Cauchy's index lemma, counting the number of sign changes you can assign to each edge around the circle. So intuitively, if you have a disk that is free, and the net force is pulling it outwards, then that means that disk wants to grow. So we should expect disks that cannot grow to be able to hold a outward force. And similarly, disks cannot shrink, be able to hold a inward force. And fixed disks can hold any force. So we can relax our matrix so that the co-kernel reflects the new kind of forces we are allowed to hold. And the way we do it is we can add additional rows for each constraint disk that can grow, shrink, or fixed. And for each disk that is not free, we add a row with 1 on Ri and 0 everywhere else. Once you patched a 1 there, you no longer require that column to sum the previous terms in the column to sum to 0 in the co-kernel. So now you relax the co-kernel. We can denote this as R extended of P. Then we can prove the following theorem. A circle packing is infinitesimally rigid if and only if the following conditions hold. The packing is infinitesimally rigid when all disks not free are fixed. So you treat all the disks that can only grow or shrink as fixed disks. Then that if that implies infinitesimally rigid, this condition is satisfied. The second condition is there exists a force density on edges such net force is 0 on each xy direction, and the inward-outward force balance is positive on shrinking disks, negative on growing disks, and 0 on free disks. So the first condition is trying to kill infinitesimal motions that can fix all the radius with a constraint. If your free disk can all move by themselves, then you are screwed. And this can be tested quickly through computer by computing the dimension of the kernel of the extended rigidity matrix. The second condition kills all infinitesimal motions with a strict radius change in the right direction. And the proof is very similar to that of Roth-Whiteley with only a small change. So for the if direction, if we can find the stress with the correct sign, then we can define omega k to be the radial net force, basically inward-outward force sum for each vertex. Then omega vector that is consisted of omega ij, where ij's are indexed over edges, and omega k, where k is indexed over disks that are not free, will be in the co-kernel, because that's basically how our co-kernel is defined. Then we can use omega times the extended rigidity matrix times p prime, and we get this term over here. So the first part must be 0 by the very definition of infinitesimal motion, because each term here being 0 is the definition of infinitesimal rigidity. Sorry, it's the definition of infinitesimal motion. The second term is non-positive because we assumed omega k and rk prime have opposite signs. The reason is if rk prime is positive, we are allowing it to grow, then it can only hold negative polar force. On the other hand, if rk prime is negative, the disk is shrinking, then we only allow it to hold positive force. And as a result, if any r prime is not 0 here, that would give us a strictly negative term. And this contradicts the fact omega is in the co-kernel, because co-kernel times the extended matrix is 0. You can't be negative. So all the r primes have to be 0, which says if you can find such a stress with correct sign, you cannot change any radius of constraint disks. And by condition 1, if this is true, we say that infinitesimally rigid, so we have infinitesimal rigidity. The other direction is slightly trickier. The condition 1 is automatically true, because if we treat all the growing disks and the shrinking disks as fixed, that only makes it more rigid. So 1 is automatically true. To prove 2, the existence of a stress with correct sign, we employ the Fredholm alternative. This is a lemma that says either ax equals b has a solution, or there exists a y such that a transpose y equals 0, but y transpose b is not. Then we let A equals the transpose of our extended rigidity matrix. Let B be any number we assign to one of the free disks. We can think the number in B as a growth shrink factor that we assigned to a free disk. And we want to say, well, our system is able to hold that free disk from changing. The lemma above says either there's an infinitesimal motion fixing all non-free disks that strictly modifies, which is why TB is not 0. It's not 0 because it strictly modifies on the disk. Or an internal force can prevent the free disk from deforming. That is saying AX equals B has a solution to counter any B. Since our packing is infinitesimally rigid, the only possibility is the latter case. That is to say, we can find an internal force that prevents one of the free disks or any set of free disks from changing. notice here, this stress, we didn't require any sign on it. So we're just saying there exists a stress with any sign that can counter the desire of changing for free disks. The idea is that we want to assign the growth and shrink factors on the growing and shrinking disks. Then we want to show that we can find a stress that with the correct sign that counters that change. Then we can take the linear combination of the two stress, and we can multiply the stress with correct sign by a very large number. Then surely, once you add them up, you have all the correct signs. To do that, we employ the Parker's alternative. Either Ax equals B has a solution, X is strictly positive, or there exists Y such that A transpose Y is not positive, but Y transpose B is greater than 0. Actually, all we need is Y transpose B is not 0. Again, we let A equals the transpose of the rigidity matrix, and we modify the signs of the rows because we want our Y, A transpose Y, to be all of one sign, to be non-positive. So shrinking disks, they are fine by themselves. Growing disks, you flip that row. And for fixed disks, you are free to choose either sign because fixed disks can hold any kind of stress. So feel free to pick whatever sign that eventually would work for you. Then the lemma above says either there is an infinitesimal motion moving a growth shrink disk in the correct direction. So this is, I think, A transpose Y less than or equal to 0, less than or equal to says it's moving in the correct direction. Or there exists an internal force with correct signs to counter the radial forces of growth shrink disk. That is saying Ax equals B, because once you assign B on growing and shrinking disks, you can find a solution X to counter it. Since our configuration is infinitesimally rigid, only the latter case can be true. That is, you can find Ax with the correct signs. Then the finish is proved. You can multiply this stress you find by a very large positive number, then take the linear combination of the stress you find previously to counter all changes of the free disks. Okay, so that's the end of story for infinitesimal rigidity. The next business is global rigidity, and here's a picture of a black hole. I'm using this picture because global rigidity feels like it's just sucking my energy in, and there's barely any outcome coming out of it. But it's not completely black. Some configurations, it's globally rigid. For example, for this figure on the left, we want to grow all the disks on the boundary, and we want to shrink in the interior, and we have 6 free disks. This cannot be done because it is well known that the entire packing is determined by boundary radii, and all the partial derivatives of partial interior over partial boundary is positive, which means increasing all the boundaries will increase all the interior, and you can't shrink those 5. That's not allowed. So we have a global rigidity statement for this very special case. That is also globally rigid. So based on the arguments from previous slide, 2 and 5 cannot both grow or shrink. If they are both red, you have a red ring surrounding a blue. If they are both blue, you have a blue ring surrounding a red. And by the argument we previously have, that's not allowed. So the idea is, without lots of generality, we assume one of them is shrinking, let's say 5, and the 2 is increasing. Then we can compute a lower bound for the size of 2 by assuming 1, 3, 4, 7 are fixed. Because if 4 is growing and 1, 3, 7 are shrinking, and 5 is known, then 2 has to be very large. 2 have to grow large to compensate for it. So if you fix all of those, you get a lower bound, let's say the lower bound for the size of 2. And similarly, by fixing 4, 7, 6, 8, 10, 9, you can compute a upper bound for the size of 2. given size of 5. And the interesting part is if you align the two curves together, the lower bound is higher than the upper bound unless 2 and 5 are equal. So that says actually 5 cannot shrink at all. Because if it shrinks, then the possible 2's lower bound is higher than the upper bound. So that gives a global statement for this packing. But in general, I don't have an argument because you can clearly see I'm exploiting the special configurations I have. This one is very simple. There's only 2 disks that are free, and that one has the entire boundary moving in one direction. So why does global rigidity matters? If we can determine the global rigidity for these packings, then we can assign minimal disks to grow and maximal disks to shrink. And this allow us to examine how uniform packings can be given a finite graph. And if we can show sufficient many finite graphs cannot be too uniform, we have insights into what kind of graph should look like if we want our packings to be uniform. For example, if we want an infinite triangulated packing of the plane, and if many finite packings cannot be too uniform, then those graphs cannot be the subgraphs of the infinite packing we want. Here's a conjecture. The packing on the left found by Fernick has the maximum uniformity for any plane triangle packing. That is not hexagonal. I think the radii ratio of Rm over Rmax is about 0.651. It looks very wild. Why would this conjecture ever be true? Because what he did is he just enumerated all the triangular packing of 3 sizes, and that's the best for 1, 2, 3 sizes. And why would that be the best? Why wouldn't it be better with 4 sizes or 5? And the reason I believe it's true is that I actually have a collection of finite packings, which I optimized through a computer with interior point method. And as far as I can see, they should be global rigid, but I don't have. And if they are, their uniformity is actually worse than this. And if we kill all these configurations, you can actually show the only planar triangulation is isomorphic to this triangulation. But this is a periodic packing. With one triangulation, you have only one packing, so it's unique. So if my collections are globally rigid, then this conjecture would be true. Okay, so there are some references. There's some minor references I didn't add. Those are the major ones. Thank you for showing up.
Thank you. And I'll ask for questions now.
I would love to see a sculpture like Tensegrities around the country with your circles.
Well, actually, I have an animation of basically showing you why this is globally rigid. Let me find the program. Stop sharing this screen, and then can you see my screen for Mathematica?
Yes.
So I use a different basis. Here, 6 wants to grow, and if you did grow 6, then boom, 3 actually grows larger than what it's supposed to be. And then again, if you increase 8, 3 is screwed. And if you shrink 7, 3 is screwed. And if you increase 10, 3 is screwed. And if you increase 9, 3 is also screwed. And 2 is this free disk. It can go both ways. And if you go both ways, 3 is screwed. And 4 wants to grow. And if we grow 4, 3 grows. And 1 wants to shrink. If you do that, 3 grows. So it's clearly any kind of motion on this basis will actually screw 3.
take, yeah, go ahead, Ken.
Yeah, if we go back to the one that you're looking at with Fernique's conjecture, are you saying in that picture that if we look at that, I guess a torus packing, if you want to use a periodicity, a torus packing, and that one you'd like to show is rigid? Is that?
I would like to show that if you want the minimal disk to grow and the maximal disk to shrink, then it's rigid.
I see. So, I mean, that's the specific combinatorics that are of particular importance here.
Right.
Yeah, yeah. Okay, thanks.
Right. So isn't it true that you can show locally that it is rigid, right?
Yes.
It's infinitesimally rigid. You want to show globally it's rigid.
Yes, I want to, actually, I only need global rigidity for finite packings. Packings like,
That's yeah.
like this and that. If I can find, for example, if I can prove this one is globally rigid, this one right is globally rigid, then its radii ratio is worse than Fernique's, then I proved that you cannot have this finite graph as a subgraph. So I want to eliminate enough finite subgraphs from all the possible planar triangulations.
This is an old problem of Laszlo Fesch-Toth in his book on, what is it, regular figures.
Yes, and he was wrong.
Yeah, he was wrong. But it was his best guess. He didn't claim it was wrong. It was right. Right, he had a list of his best guess for certain ratios of radii. And he did not, Fernique found this, and he didn't, Laszlo Fesch-Toth didn't know about this. And we think this is the best, for a triangulated packing, that this is the best triangulated, the best, largest ratio, closest to 1.
Right.
That is triangulated. And so its density is bigger than pi over the square root of 12 because it's triangular.
Right. So if this conjecture is true, then all the packings with good densities are approximated or somewhat a flow, a flip and a flow from triangulated packing. So this can be a very good estimate of the upper bound allowed. And I believe if you want to beat pi over square root of 12, your radii ratio cannot beat this figure by a lot. Maybe you can beat this by 0.0 something, but definitely not a lot.
Right, right. We have our best guess, just like Laszlo Fesch-Toth, about what the, by doing a little bit of flip and flow so that it's still, at the limit, it's pi over the square root of 12. We think that's the best you can do. Anything above that ratio, you might as well just make them all the same.
What's the ratio in this picture?
Is
that
about 0.651.
Right. And the best ratio we think is 0.651001 or something. It's very close to this. But the best ratio is not triangulated. But it's almost triangular, not far.
Yes, you can simply shrink the maximal disk here by a little bit, then that gives a better ratio.
Yeah.
I have a general question. If you have a packing which is rigid but not infinitesimally rigid, this basically means that linearization of the contact equations does not deliver enough information. Can you find criteria involving higher derivatives?
If it's infinitesimally rigid, you can't find anything nearby.
Oh, I mean, this one
Yeah,
is.
but I mean, it is not infinitesimally rigid.
Yeah, this one is not infinitesimally rigid, but it's locally rigid. It's definitely locally rigid because we showed this actually globally rigid. What's the criterion for rigidity? I actually don't know.
Well, even for tensegrities, the condition for local rigidity beyond infinitesimal rigidity gets complicated. There's these what do you super universally rigid, super stable, pre-stress stable. There's a whole zoo of criteria for the thing to be locally rigid, and it's still not enough. There's still it's not enough for what people want.
Mm-hmm.
So sorry, I don't know a criterion to determine rigidity, really.
Mm-hmm. But do you think higher derivatives can help?
Actually, I haven't tried. But in tensegrity, I don't think second order rigidity implies rigidity. Oh, they do, but they're still not the same. And I don't think that would be the case in here.
Okay, thanks.
Yeah, this thing on the left, why that thing is rigid, that's kind of mysterious. He has a proof, but right.
Yeah, the proof exploits the special structure. It doesn't tell the nature why it's rigid.
Yeah, I have certain themes I keep coming back to, sorry. And I've talked with you briefly about this, Albert, because
Right.
if you think about adjusting a boundary circle in the packing, and you can lock in the other boundary circles.
Right.
And then you see what things have to change, or whether you can drive the change all over to 5. And somehow you can't drive all the change to 5 if you lock the others.
Right.
3 is forced to do something. I don't know if this idea can be extended beyond this one, but if you think about your first statement regarding this one on the left, that if 2 and 5 are fixed, then you have the ring around 7, which is fixed, so 7. And if 2 and 5 are fixed, then the ring around 4 is also, you have a whole boundary.
Right.
Right.
And so, yeah, in the graph, you have these subdomains where if you modify something on the edge, it has to go through, it has to go break out somewhere. And so I don't know if there's a sort of electrical circuit analogy that would be useful. It's probably just a reformulation of your matrix, your rigidity type matrix. So I don't know if there's anything in there that's helpful, but I think about it in those terms.
So our strategy right now to prove global rigidity is to try to find some kind of potential function that is minimized over given configuration. But the stress energy that is used in tensegrity sort of doesn't work. If you apply the same procedure, you get a quadratic form that is always 0 on odd circle packings. So that doesn't help